I like to start in the solar system, where we do know a lot about the planets there, about the bodies there, and put that in perspective with exoplanets. So here I put the 8 solar system planets in the mass, distance to the star diagram, and I add about 2,000 exoplanets. And the sky blue ones are the ones that are detected in transits. And as was nicely explained in Niku Madhusudan's talk, these guys are important for the atmospheric characterization. And what we are able to do right now is to characterize hot Jupiters. And Niku showed you a very spectacular example of this kind of characterization. I'd just like to add that this kind of studies will be routinely achieved with the James Webb Space Telescope down to Neptune mass planets at least. And tomorrow, where we would like to go is there to characterize Earth-like planets. Just for the sake of simplicity, let's assume that Venus and the Earth are alike, even though you know that it's not the case at all. And well, this is going to be a huge challenge. Actually, in my first paper as a PhD student, which consisted in simulating the transmission spectrum expected for terrestrial planets. In the conclusion, I wrote that you will need a 30 to 40 meter telescope to probe Earth-like atmospheres around Earth-like planets. And these numbers, 30 to 40 meters, suppose that Earth-sized planets are frequent and are efficiently detected by surveys. And what I did mean by 30 to 40 meter telescope is a 30 to 40 meter telescope in space. So we are well aware since several years that this is going to be extremely difficult to achieve. And it could be seen as actually as a kind of a pilgrimage to detect life in the universe in the atmosphere of an exoplanet. And like with pilgrimage, what is important is not really where you want to, not really getting to your destination, but it's the path that is important and what you learn in the way to your destination. And in this case, there could be several ways that could be attempted to reach this goal through transit spectroscopy of hot super-Earth and Earth, or through direct spectroscopy of young and hot giant planets, for instance. And the first step toward characterization is simply to get the planet bulk density. So it's, in principle, it's very simple. You just get a mass measurements with radial velocity from high-resolution spectrograph on the ground, and you get transit measurements, and you infer the radius of the planet through the transit depth, through the transit light curve, and you get the bulk density. And here in these plots, this is the radius of the planet, mass of the planet, and the size of the symbol is proportional to its density. So the bigger, the denser. And I've put the solar system bodies in these different quantified categories. I also added the icy moons that Olivier Grasset told us about yesterday. This is Io, this is the moon. And now I will add the confirmed planet for which we have both a radius and a mass. And you can see that on the number here are the bulk densities actually in grams per cubic centimeters. And you can see right ahead that there is a huge diversity that does not exist in the solar system. And we are used to define these categories in mass, super-Earth, Neptunes, subgiants, and I'd like to focus on this part where there is a huge diversity, and where a legitimate question is what are these different bodies made of? So this is a very simple sketch for terrestrial ice giants and giant planets, and we have now new categories in between, and there's a lot of exotic internal structures that have been proposed to explain this diversity. Gas dwarf, giant telluric planets, mini-Neptune, ocean planets. And it sounds very exotic, and we have few constraints on that, but there is actually name tags for each of these categories where we think we could explain the measurements by this kind of structure. And all the constraints we could ever draw on this are based on the bulk density. Now, I'm not saying that by measuring the bulk density, you will identify a unique internal structure profile. It's not possible. There's a lot of degeneracy. But every modeling work has to start with a good measurement of the bulk density. And another question is how, if you think about the time evolution, how do these planets evolve? You may have noticed that most of these objects are detected very close to their stars. So far, it's an observational bias. But it means that the star has a potentially tremendous impact on the evolution of these bodies. And we know since the beginning of the 2000s that there is an impact, there is atmospheric mass loss, what we nickname evaporation, and the question is whether this evaporation could lead to, for instance, to get rocky planets out of planets that were once more massive with a gas envelope and could even be destroyed by extremely strong irradiation of the star. And let me just give you one recent example. Here, in this case, so this is far ultraviolet observation with the Hubble Space Telescope. We monitor the Lyman alpha emission line of the star, and we are looking for an absorption during transit. And it turns out that when this particular star, so HD 189733b, is active, as shown by the detection of a flare in X-ray contemporaneously to the HST measurement, we see a significant absorption in the Lyman alpha line, which is interpreted as a huge cloud of hydrogen that is escaping the planet. And in this case, we see different cases where there's, depending on whether the star is active or not, inferring temporal variation in the atmosphere as a result of stellar activity. There are other cases in the literature where we see this huge absorption, and we think that this is something that is common for hot Jupiters. So Niku presented you this sketch, so I will not spend much time on it, simply telling you that I will focus here mainly on transit transmission spectroscopy, so studying the atmospheric limb of the planet during transits. And well, we need transit to do that, obviously. And what the Kepler mission, the NASA Kepler mission, has brought us is really a revolution in terms of number of transiting planet candidates, more than 4,000. All these white pluses here. So here it's the radius, not the mass, because for most of these objects, we don't know the mass. The stars are too faint to even measure the masses. But it's very interesting statistically what you can say about this population, but you need a critical information, which is the mass, without which you cannot infer the bulk density. And all these detection makes the transiting planets pile up at very faint magnitude, here in this histogram plot, whereas planets for which we have mass measurements tend to pile up at bright magnitudes. And only for these planets here at the intersection, you have both mass and radius precisely determined, hence a bulk density. And this is what the next set of space mission is looking to improve, to have planets with precise radii at around bright magnitude stars. So which planets can be actually studied? Well, this plot here represents the near-infrared magnitude of the host star as a function of the transmission signal one would obtain from 1 atmospheric scale 8 of the atmosphere. So in transmission spectroscopy. And the line here, this is the 3 sigma detection limit of Hubble. Now this is the expected 3 sigma detection limit of the James Webb Space Telescope. And again, the size of the bubbles is proportional to the mean density, to the bulk density of these objects. So in Niku Madhuson and Stoke, you had a lot of results on these two planets. Well, it's no surprise since these are among the very best targets you can probe their atmosphere with transmission spectroscopy. And it showed you this water detection in the near-infrared with Hubble for HG209458b. And you may notice that there is a kind of a gradient in the size of the bubble going from left to right. And this is again expected because actually the bulk density matters when it comes to atmospheric studies, because this quantity here is proportional to the temperature, inversely proportional to the bulk density, to the atmospheric composition, and it has also a strong dependence to the stellar size. So the least dense a body is, the easiest it is to characterize its atmosphere. And let me just now filter out the hot Jupiter, the giant planets, to focus on super Earth and Neptune. So this is what would left. So you might think, okay, we have a handful of planets that are good, that would be characterized by JWST. But here I'm cheating because I'm making a strong assumption that the atmosphere of this object are exclusively composed of molecular hydrogen. And while you could say, okay, this might be okay for Neptune mass objects, for super Earth in blue, clearly it's a bit of an extrapolation. And actually, if you assume that some of these objects are dominated by H2O rather than H2, then you lose a factor, an order of magnitude in the characterizability of these objects. And they are much more difficult to observe. And for super Earth, it's even worse, because if you think that, okay, these guys are not super Earth, but super Venus with CO2-rich atmosphere, it brings them down to the point where even the James Webb would not be able to characterize them. And this is an example that was shown by Nico as well, GJ1214b, for which even though we reach a very impressive precision of 30 ppm per spectral channel, we have a flat line from which we infer the presence of clouds. And we don't know if these clouds will be found we don't know the fraction of planets for which we will have this cloud preventing us to observe the atmospheric constituent at lower resolution. This is a case where the clouds are not apparently preventing the detection, but this is the only case we have for a hot Neptune. And clearly from that we need more bright targets. And this is the goal of these 4 missions that the community has managed to get through the selection process of space agency. So K2 and TESS are NASA, and KEOPS and PLATO are European Space Agency. And I will just describe in a nutshell these 2 European missions. So KEOPS, with which I'm pretty much involved these days, is Europe's next exoplanet mission. It's set for a launch in 2017. It's the first small class mission of ESA, and it's a joint project between ESA and the consortium of ESA country members that is led by Switzerland. There is a strong participation by Portugal, which is providing the mission planning scheduler tool and the data archive software for the ground segment of the mission that will be located in Geneva. It's a follow-up machine, which means that it will perform first-step characterization for already known low-mass exoplanets. And it will collect what I call the golden target, the most amenable target for future atmospheric characterization, for instance by the James Webb, but not exclusively. And it will allow 20% of open time for precise photometric studies. How it will do it? It will do it by collecting a precise transit light curve for radial velocity planets detected from the ground around bright stars for which we don't know if the planet transits, for instance, or by obtaining higher precision on the planets detected through transit surveys. And it will do so using high precision photometry from a 30 centimeter diameter space telescope that is set on a sun-synchronous orbit at around 700 kilometers in altitude. So the total budget of this small mission is around 100 million euro, and the big challenge is that the ESA share of it is capped to 50 million euros, which is small for the agency. And the other challenge is that the whole thing has to be developed and launched within 4 years, which means that since we were selected in late 2012, we are already now approaching the critical design review of the instrument. So it goes very fast, and so it's set for a launch at the end of 2017, and the mission will last 3.5 years. Now PLATO. So PLATO is an M-class mission that is set for a launch in 2024, and it could be seen as the habitable zone explorer, because in fact, in this stellar mass semi-major axis diagram that I think was shown also in some previous talk, well, the space of parameter where KEOPS, TESS, and K2 will bring planets amenable to further detailed studies is quite limited in range, and it will barely go to the habitable zone. For TESS, there will be a handful of habitable zone planets, but no more. Whereas PLATO will cover everything. We'll cover the habitable zone of Sun-like star, and we'll cover beyond the habitable zone for later type star like N-dwarf. And it will do so by performing a survey over more than half of the sky. And you can see here the big difference with Kepler. This is the Kepler field here. And so this is the PLATO field of view, and the PLATO field of view will be moved during the mission and took over one half of the star. And the setting is very interesting because there is 32 cameras which have overlapping field of views, and that gives PLATO a very high photometric precision to detect transit of Earth-sized planets. And the expected yield of PLATO can be represented this way. So it's only for the brighter stars. It's much more, these figures are much more increased for fainter stars, but for the brighter stars, you can see that here you have the separation that is normalized so that one is always in the habitable zone no matter what kind of star you have. And this is the mass of the planets. So you will have, for instance, 30 Earth mass planets in the habitable zone of stars that are bright enough to do atmospheric characterization. And for all these objects, thanks to the precision of PLATO, you will have the radius, the radii of the planet down to 2% precision. You will be able to follow up with radial velocity on the ground to get masses to 10% precision. And because you have photometric precision, you will be able to do astroseismology, which will bring you the ages of the system to 10%. And that's really awesome because, well, it means that basically you will be able to study early Earths. And you will know that and what stage they are. Okay, so actually PLATO will be, we expect so much from it that it will put you in a very strange situation where right now we are, the field of atmospheric characterization is target starved. We don't have we don't have enough targets into a situation where we will face basically a flood of objects, and the question is, will we be able to characterize the atmospheres of all these objects with the facilities that exist now and that will exist in the future? In other words, are we ready to exploit the harvest for all these missions? And this is not trivial because if I put this mission in a timeline here that goes pretty far beyond 2030s and so on, well, you can see that so the big change will occur with PLATO starting 2024. And let's first just focus on the before PLATO. Then where here you see that it's about okay from a space-borne perspective because TESS and KEOPS, actually KEOPS will follow up TESS targets, will be contemporaneous with Hubble, that is poised to stay up to 2020, and on the James Webb. But beyond that, beyond the start of PLATO, then we may have a problem because if James Webb is not extended, then you don't have a spaceborne facility able to characterize PLATO planets. And that's where a new perspective has recently come from considering what we have on the ground and what can be the contribution of ground-based instrumentation to the atmospheric characterization of in particular PLATO planets. And this is I will exemplify this by showing you a result that is using two things that are possible to do only from the ground right now. It's high dispersion spectroscopy and high contrast and high angular resolution imaging. And the example is, so it's on one of the most famous stars in the sky, Beta Pictoris, which was the first stars around which in the early 80s, using the first coronagraph, Smith and Terry detected a circumstellar disk. So it's a debris disk, so posterior to the formation of planetary system. And in data from 2003, using adaptive optics at the Very Large Telescope, the team of Anne-Marie Lagrange, and I was lucky at the time to be postdoc in this team, detected an object here aligned with the disk, and in later in data obtained subsequently, the object was found moving around the star with on an orbit that was very much compatible with the Keplerian orbit, aligned with the disk. And so this was the first evidence for a planet within disk, and the planet is a giant, giant planet, about 10 Jupiter mass, and it's a young planet, below 20 million years. And so, of course, if you observe on now with the third generation of adaptive optics imager, you have it's almost routinely detected. It's very spectacular. Here it's Gemini GPI first light observation. Expects other spectacular images coming from the SPHERE instrument that was recently commissioned at the VLT. And of course, if you observe this in different passbands with different filters, you could already build an emission spectrum of these giant planets. But we can actually go farther than that, and that was the idea of the team led by Ina Snellen in Leiden, was to put the slits of high-resolution near-infrared spectrograph both on the star and the planets, and try to spot a signal from the planets. And what they did, so here is the slit image, and you have the spectral dispersion in this direction. So of course, with this kind of setting, you cannot detect the planet because the contrast with the star is too big. But the clever idea was to, at each spatial position along the slit, to cross-correlate the signal with a template carbon monoxide spectrum. So you do not expect to have carbon monoxide in the star, whether you could expect to have it in the planet. And it turns out that at the expected position of the planet, you got the peak of the cross-correlation signal. And it's an almost straightforward observation, half an hour observation, and it leads to when you fold this and you look at the velocity or wavelength signal to see this average line, the cross-correlation function, that is broadened with respect to the instrument resolution, and that led Withertor to infer rotation speed of the planet that is about 25 kilometers per second, which means that it has a rotation period of about 5 hours. And it was the first detection of the rotation, the first measurement of the rotation period of an exoplanet. So this is an example of what a combination of technique can bring to the field of exoplanets. And well, the good news is that on top of this instrument, TriRace, which is set on one of these giant telescopes at the VLT, well, there is a whole lot of high-resolution spectrograph which are stabilized in pressure and temperature and use optical fiber that are already in operation. Among those, HARPS, which is our Swiss built instruments that is now detecting all the radial velocity, most of the radial velocity planets. And a lot of these high-resolution spectrographs are set at 4-meter telescope. And the purpose of that is mainly to follow up the candidates for TESS and for PLATO, to prepare for PLATO, to measure the mass. But as I will show you, we can do more. And of course, I would like to mention as well that there will be also the super ARP installed on the VLT, which is called Espresso, which will be able to collect light for both unique telescopes at the same time to measure the radial velocity variation of Earth mass planets. And let me show you how these instruments, this high-resolution spectrograph, can be used to achieve atmospheric characterization. So this is the transmission spectrum of this planet, HD 189733b, as seen by the Hubble Space Telescope, collecting 3 transits at a medium spectral resolution in the visible. And here you have the signature of the sodium doublets, which is one of the most robust signatures of exoplanetary atmosphere. And this is very interesting signature because the sodium doublet is a probe of the upper atmosphere and it can be observed above the cloud layer. So no matter the cloud coverage you have on an exoplanet, you should still be able to infer the properties of the upper atmosphere by detecting and measuring these two lines. And nobody could argue against the fact that, well, this is a sodium signature. There's no ambiguity here. And for instance, but the kind of constraint you could infer from a spectrum like that are pretty rough. And this is basically the temperature gradient in the atmosphere. You have the temperature with respect to altitude in the atmosphere of this planet. And okay, there is a hint for a temperature rise in the upper atmosphere. Let's now look at what we have been able to achieve very recently with HARPS. So HARPS is on the ground, but on a 3.6 meter telescope. Hubble is 2.4 meter. And it has a much higher spectral resolution. And at this much higher spectral resolution, taking care of dealing with telluric contamination, which is the major limitation of observation from Earth, Aurélien Wittenbach, a PhD student in Geneva, has derived this gorgeous transmission spectrum of the atmosphere of the planet. And here, basically, we have a 10 sigma detection of the lines that is compatible with the Hubble one. The sensitivity is similar, to my surprise. And in addition of that, the resolution is 20 times better. And actually, we do resolve the line of the planets by a factor of 10, and we measure a ratio in the two lines, which is difficult to explain actually. So it's very interesting, and we think that this is a sign, a strong sign for having a temperature gradient. So you can start to do with this kind of spectrum. You can start to do line fitting as you would do in a stellar atmosphere. And I won't expand a lot, and this allows us to retrieve a very nice gradient in the upper atmosphere of this planet. And you might wonder why these temperatures are reaching so high level in the upper atmosphere, like 3,000 Kelvin. Well, in a way, it's expected, because if you remember, this is the same planet for which I showed you that you have atmospheric evaporation. And atmospheric evaporation or mass loss requires to have, okay, I'm almost done, to have very high exospheric temperature of the order of 10,000 K. So this kind of observation at high spectral resolution actually could bridge the observation of the lower atmosphere that Nico Madhusudan presented you to the observation of mass loss on Jupiter. And this is possible today from the ground in the optical. So so I got just two more slides, and this one will be very short. The very nice perspective here is that you see that all these arrows extend up to the PLATO era. They are ground-based instruments, so they could basically live forever if there are no budget cuts. And we could expect a lot of things coming up from the what we call the extremely large telescope, 30 to 40 meters in diameter. So remember, 30 to 40 meters in one of my first slides. Well, here we go. If Europe is able to build this extremely large telescope, and we have high resolution capability on it, then we could be able to do much more than probing hot Jupiter. And this was there was a simulation done by the Snell group, who in a nutshell showed that you could detect molecular oxygen in the atmosphere of an Earth analog around a red dwarf with the European extremely large telescope. You could retrieve a signal by accumulating 30 transits of such a body. Here are my concluding remarks. So the atmospheric characterization of hot giant planets is ongoing now from the far UV to the near infrared. We are on the verge of being able to characterize Neptune-mass planets, and we have more results coming in the coming months. And the characterization of Earth-sized planets in the habitable zone will actually be possible in the 2020s, assuming we have enough bright targets found, and this will be the job of this already accepted mission here upstairs in PLATO, assuming that we can filter out what are the best targets to be observed with the E-ELTs or James Webb, and that would be possible thanks to surveys that could be carried by 4-meter or 8-meter ground telescope, as I exemplified, and providing that high-resolution spectroscopy is available for the E-ELT. And I'd like to finish by pointing out that if you are to find life on a nearby exoplanet, well, to me it's a very exciting perspective to know that this exoplanet will be most likely known by 2030 because of PLATO. Thank you.